Hey everybody. Today we're talking about the standard normal distribution. And this is just the normal distribution, or bell curve, with mean 0 and standard deviation 1. So the peak of the standard normal distribution is at 0, and the points of inflection are at positive and negative 1. And by point of inflection, I mean a place where the graph changes curvature, where it changes from looking like the top of a hill to the bottom of a valley. It's traditional to use the letter z to refer to a random variable with the standard normal distribution because of this fact. If you have a random variable x that has any normal distribution with mean mu and standard deviation sigma, and you use the formula for a z-score on it, x minus mu over sigma, to get a new random variable z, then that new random variable has the standard normal distribution, n of 0, 1. For any particular x value in any normal distribution, we call the corresponding value x minus mu over sigma the z-score, or standard score. And the z-score represents the number of standard deviations by which the observation x lies above or below the mean. The probability that a randomly selected z-score lies in a certain range is the area under the graph of the standard normal distribution over that range. So here I'm showing you the probability that z is between -1 and positive 0.5, and I've done this by graphing the standard normal distribution, labeling the points z equals -1 and z equals 0.5, drawing vertical bars there, and shading the area in between. As with any continuous random variable, the total area under the density curve is going to be 1. Roughly speaking, when you do a probability experiment, something happens with probability 100%. We compute standard normal probabilities using the cumulative distribution function, or CDF. The CDF gives the probability that the random variable in a particular trial comes out to be less than or equal to whatever value we specify. So you give me a z value, I label that on the horizontal axis, and then shade all of the area to the left of that z value. The shaded area is the probability of getting a random standard normal value less than or equal to that z-score. It's traditional to use the notation phi of z, with a capital Phi, for the CDF of the standard normal distribution. So when you see phi of z, you're seeing the probability of getting a random z-score less than or equal to the z that's specified. So for instance, here's a picture of phi of 0.5, the probability of getting a z-score less than or equal to 0.5. And we can estimate such a probability just visually by estimating what fraction of the area here is shaded. And just visually, I'm going to say it's about 70%, so phi of 0.5 is about 70%. Now, statistics books always include tables of values for phi of z, but the calculations are best done using technology. R is totally typical, that's my technology of choice. The command for the standard normal CDF is pnorm, and all we have to do is feed pnorm the z-score that we're interested in. For instance, to find phi of 0.5, the probability that z is less than or equal to 0.5, we just enter pnorm of 0.5, and we get 0.691. So a little bit less than my visual estimate from a couple slides ago. Here's a picture of that probability, phi of 0.5, pnorm of 0.5, the area to the left of 0.5 is about 0.691. To compute the probability that a z-score falls in a certain range, we start with the probability that the z-score is less than the right-hand endpoint, and then subtract off the probability that it's less than the left-hand endpoint. So we do phi of b minus phi of a. And geometrically, that means subtracting the area to the left of a from the area to the left of b. For instance, the probability that z is between -2 and 0 is phi of 0 minus phi of -2. So I'm taking the area to the left of 0, that's pnorm of 0, which by the way is going to be 50%, and then subtracting off pnorm of -2, so the area to the left of -2. I do that arithmetic, and I get 0.477, 47.7%. Two useful facts to remember when computing in the standard normal distribution. First of all, since we're in a continuous distribution, probabilities of particular z-scores are infinitesimal. So you don't have to worry about whether your inequalities inside of a CDF are strict or not. The probability of being less than or equal to a certain value is going to be just the same as the probability of being strictly less than that value. Secondly, to find the probability of getting a random z-score greater than a particular value, you can do 1 minus the probability of getting a z-score at random less than that value. And the reason is just that the events z greater than the value and z less than or equal to the value are complementary. So the formula there you're seeing on the second bullet point on the left is just the rule of complements. For instance, to do the probability that z is greater than negative 1.5, we do 1 minus the probability that z is less than negative 1.5. 1 minus phi of negative 1.5, 1 minus p norm of negative 1.5 is 0.933. So this probability is about 93.3%.